In this problem, I'm going to factor the expression x to the fourth minus 256. Right away, I notice that this looks like it's going to be a difference of perfect squares. That's something you want to be able to recognize when you're looking at a difference of perfect squares, because there's a special identity that we could use. The identity is, if we ever have two perfect squares being subtracted, then they will break down into a plus b times a minus b. Now, how do you know whether you have perfect squares or not? You could create a tree for the different elements here. I'm going to create a factor tree for x to the fourth and a factor tree for 256. So x to the fourth is made up of 4 x's being multiplied. If I split them up into two groups, then we see that x to the fourth would actually break into x squared times x squared. That reveals that x to the fourth is a perfect square because it could be thought of as something times itself. When it comes to 256 happens to be 16 times 16. You could do that on calculator. Just take a square root of 256 and it will tell you 16. So we clearly have a difference of perfect squares. Now, if we match up the expression that we're given to the known identity, we can see that x to the fourth is taking the place of a squared right now, and the 256 is taking the place of the b squared. So if you want, you can write those on the side, that our a squared is x to the fourth, and our b squared is 256. In order to complete the breakdown here, we're going to want to find a, which is the square root of a squared, and b, which is the square root of b squared. So a is the square root of a squared, which is a square root of x to the fourth. I already have the square root of x to the fourth pictured in my tree. It is x squared. So a is x squared. I'll do the same thing for b. I'll take the square root of b squared, which is the square root of the 256, and that's 16. So 16 is the b. We now want to use the identity and plug the right things in for a and b. So our a is x squared. Put that as your first term of the binomials. And then your b is going to be the 16. Put that here. Now that's good so far. We did factor our original expression into a more factored form. However, we have to look to see if we've truly factored the thing completely yet. And a sum of perfect squares cannot be factored further. Even though x squared and 16 are both perfect squares, this part of it is not further factorable. But this part is further factorable because it is another difference of perfect squares, I notice. So I'm just going to bring my results down here and keep going with the problem and see if I can break just that second binomial up into two binomials. And so this guy will now be replaced with another product of two binomials. So in this case, if we consider this part to be a squared and this part is b squared, then on the side I'll say that my a squared is now x squared and my b squared is the 16. I'll find the square root of the x squared, which is going to be just x, and then find the square root of the 16. That's 4. Now that I have that, I can take my x and my 4 and plug them in to my binomials. So we'll have x plus 4 and x minus 4. And this will be as far as we can go with the factoring, unless we were going to use imaginary numbers. But that's a more advanced topic for now. So let's just stick with this as our final answer.